Hi, I'm Dee Dee Chang, your host. In this workshop episode of Audio Builders TV, we will look back to the March of 2016 workshop, Mike Pre's A to Z. In this amazing talk, Eric Gaskells explains how the technical difference between mic preamplifiers create their sonic characteristics. Eric was involved with the design of the AEA R84 ribbon microphone and published an AES paper on the psycho-acoustics of Amp Distortion. He is an audio engineer and educator at Mcgill University. Audio Builders TV is produced by the students of Concord Carlisle High School with help from Colonial Sound and CCTV. Please subscribe to us on our YouTube channel and sign up for a mailing list at audiobuildersworkshop.com.
Audio Builders.
I want to talk about why different microphone preamplifiers sound different from each other, and look at the technical reasons why it is that that one microphone preamplifier might sound one way and another. Why does an API sound the way it sounds versus a Neve versus a CP5, or I was going to say a Doug Fern pre, but I'm actually not going to talk about tubes at all. So I will keep to what I know. Okay, next slide here. So I'm going to look at a few different designs today. I'll look at a Neve, which is basically a transformer buffered Class A amplifier. I'll look at API, which is a transformer buffered operational amplifier. I'm actually going to kind of gloss over the twin servo. Peter talked about it a little bit already. And I'll talk about also transformerless instrumentation amplifier topology, similar to the baby pre. All right. So here is the Neve 1272 Class A. You can see in the picture the Carnhill transformers, transformer buffered in and out. A single voltage power supply with a big heat sink on it because it's always drawing current. And a gain range of about up to about 70 dB of gain. So there's a bunch of other specs here. I'll gloss over it for now. But one thing that will be important as the talk goes on is the input impedance, which for this particular mic pre is 1200 ohms. That's nominal, generally taken at 1 kilohertz. All right, let's go to the next one. Here's a schematic of the 1272. We see some of the basic transistor amplifier types that have been discussed already today. We have a common emitter, emitter follower. We have also going to be important to point out some tantalum capacitors, which are allowing the bias to be set and removed. So tantalum capacitors buffering the input and the output of the pre. All right. And then the API, which has already been discussed quite a bit today, the transformer buffered op amp, the input impedance for the API is spec'd at 1500 ohms. All right. Here's the Hardy M1. Basically, this is not the twin servo that I advertised in the first slide. This is just a single op-amp version. Essentially, the same circuit as the API, but with the Hardy 990 and different transformers buffering it. Its input impedance is up here somewhere. Is it? No, that's the measurement is made with that. No, I don't see it either. All right, we'll just keep going. Jensen twin servo circuit. As my brother mentioned in his talk, the idea splitting up the gain between two op amps, so no single op amp needs to do too much work. All right, next. Okay, so now that we have that out of the way, let's talk about what makes different microphone preamplifiers sound different. Essentially, any device that is going to transmit audio, even if it's just a wire, is going to change the sound in some way. It's going to act as a filter. And nobody gets out exactly what they put in. Whether or not the difference is perceivable is dependent on the types of changes that are made. But the changes that will happen as signal is processed by a wire or a signal processor or anything that takes signal in and spits it out are going to be changes in the frequency response of the signal, changes in the amount of noise that's in the signal, and any nonlinearity or distortion that happens to the signal in its transmission. I've sequenced them here according to what I think is their saliency. So I would say that differences in frequency response are more salient than differences in noise. So small differences in frequency response are very perceivable, whereas very small differences in the amount of noise, particularly with loud signal levels, are not going to be as significant. And again, very small changes in the amount of distortion on a signal will be less significant than very small changes in frequency response. But all of these will play a factor in the ultimate sound quality of whatever microphone preamplifier we're using. All right. So we'll start by looking at frequency response and what causes differences in frequency response in different microphone preamplifiers. So we'll start by looking at frequency response and what causes differences in frequency response in different microphone preamplifier designs. Well, first thing would be intentional high-pass or low-pass filtering that has been built in by the designer to avoid certain problems. The second source of changes in frequency response would be the bandwidth limitation of any transformers that are used at the input or the output of the microphone preamplifier. And what I think is extremely interesting is the changes in frequency response that happen because of the combination of the particular output impedance of the microphone you were using and the input impedance of the mic pre itself. And I think a lot of people don't think about this, but when you plug a microphone into a mic pre, you're creating a new circuit, right? And they're interdependent, and they will change how the mic pre will change the way that the microphone performs, and as a result will change the sound of that microphone. So the input impedance of the mic pre will have a big effect on how the mic itself actually sounds. And the final source of differences in frequency response relates to what Peter had been talking about earlier, which is the gain bandwidth product of the amplifiers. Most amplifiers will have a reduction in frequency response as you increase the gain. Okay, next slide. So as far as intentional limitations to the frequency response, there's some practical limitations that as designers you have to be wary of. For example, radio frequency interference. We do not want to get RF into our design. If radio frequencies get into our design, even if they're very high frequency, they can be intermodulated down into the audio band and cause noise and other sorts of interference and problems with the circuit. So it's a good idea at the input and output of a microphone preamplifier to do something to avoid getting that high frequency information into the circuit. And if you look, I'm sorry it's so zoomed in here, but AM radio, right, we see here AM radio, is this very large bit of the allocated RF bandwidth, and it starts way down at 500 kilohertz. And 500 kilohertz is actually pretty low frequency. When we're talking about creating a 6 dB per octave filter to avoid getting any annoying interference in, we need to begin rolling off low enough that we can avoid getting significant amount of that radio frequency into our circuit, while also making sure that we keep at least 20 kilohertz bandwidth. Okay, next one. So in a typical transformerless microphone preamplifier design, you will have components that are specifically there to keep that high frequency interference from getting into your circuit as best as possible. So in this case, we have a filter which is formed from the output impedance of the microphone, creating a filter with C1 and C2 here to ground. So a resistor into a capacitor forms basically a frequency-dependent voltage divider, which we call a filter, and that will help prevent high frequency junk from getting into the circuit. This circuit also intentionally filters low frequencies because we need to be able to set 48 volts phantom power at the input here. So we have a high pass filter which is formed from this capacitor with a resistor to ground here. So it's basically, again, a frequency-dependent voltage divider which forms a filter in such a way that we have a high-pass filter. The DC that is phantom power effectively has a frequency of 0 hertz. So if I have a high-pass filter, it will be infinitely attenuated at 0 hertz, meaning that the DC here cannot pass these capacitors and cannot arrive at my instrumentation amplifier and potentially damage it. So the value of this capacitor and the value of this resistor, which also, by the way, sets the input impedance of the microphone preamplifier, will determine the low frequency extension of the design. So I want to make sure I choose values that put the input impedance of the microphone preamplifier where I want it to be, while also not having a significant amount of roll-off in the audio bandwidth. So generally I would want that to create a filter below 20 hertz. And I would want the capacitors here to be able to create a filter that at least begins to attenuate by maybe 200, 300 kilohertz. Okay, next slide. Yeah, so just talking about capacitive filtering. We had a crash course in electronics earlier today, but if we take our basic voltage divider, we have, V out is equal to R2 over R1 plus R2 times V in. We put some voltage in, and we get some voltage out. If we replace R2 with a capacitor, the capacitor has a reactance rather than a resistance. Well, easy way to think about that is it reacts differently to different frequencies. So the amount of impedance that it presents will be different at low frequencies than at high frequencies. So the value of R2, we would rewrite this equation when we're talking about a capacitor as with Z for impedance rather than R. But it will be different at different frequencies. We would have more voltage transferred, in this case, at low frequencies than we would at high frequencies. Next slide. So here is an example of a circuit which is designed to help filter out RF at the input to a microphone preamplifier. This one has both an inductor and a capacitor, giving a two-pole filter. Sort of. With that resistor across there. Anyways, the interesting thing about having to design this filter at the input to a mic pre is that you don't know what well, in this case, R2 is, because R2 here will actually be the output impedance of the microphone that you're plugging into. Some microphones might have output impedances as low as 50 ohms, some as high as 600 ohms. So that's going to change the frequency at which the filter rolls off. And you have to bear that in mind when designing this filter. All right, next one. Transformers. Up till now, we're talking about intentionally adding capacitive filtering. But transformers inherently create bandwidth limitations because they are themselves inductors. Inductors, like capacitors, have a reactance, which means that they deal with different frequencies differently. In fact, they're kind of the opposite of capacitors. So when we have an inductor to ground, it creates a high-pass filter. And that's what happens when we create a transformer. We basically are placing an inductor to ground. The coils in the transformer itself create parasitic capacitances, which will create a low-pass filter because we have then capacitance to ground. So the transformer in its windings has the intended inductance, which creates the currently magnetic field in the core and transfers our signal from one coil to the next. And that creates a high-pass filter, but also the coils themselves create parasitic capacitances, which create a low-pass filter. So we get bandwidth limitations from the transformer naturally. That has certain benefits and potentially certain drawbacks. One benefit is that we don't need to add capacitors to block DC, the DC 48-volt phantom power from getting into the mic pre anymore, because the coil of the transformer does that for us. But I guess we also don't need to intentionally block RF either, because the parasitic capacitance of the transformer will act as a low-pass filter, assuming that it is the transformer has been made well enough that it has a wide enough frequency response, the frequency response like we want for our audio. Okay, next slide. All right, so those are sort of our intentional frequency response alterations in a mic pre. There's also, as we mentioned, the gain bandwidth differences, whereby a lot of amplifiers will reduce in their bandwidth as we increase the gain. I won't go into this too much because I think Peter did a good job of explaining it already. But we can see this example of an INA 217 where at 60 dB of gain it has about 100. It starts rolling off about 100K, whereas with only 20 dB of gain, it's flat, well past 1 megahertz. And this is a modern instrumentation amplifier. We're talking about individual op amps, some of them without that much open loop gain. We can have visible roll-off within the audio bandwidth at gains of 40 dB and above. Great. And here's some examples of that. We have, I think my brother kind of stole some of these from me, but we could see some measurements made of Neve, API, Hardy, and BB Pre, which is basically an old instrumentation amplifier style design that we did several years ago at minimum and maximum gain. The Neve actually, because of the way the gain is done, doesn't change until the last few high gain positions. So for the Neve, we see it move from, I think, 56 up to 70 dB of gain. And with each increase in the amount of gain, we get more roll-off. The Hardy, we see roll-off as well. These graphs go out to 200 kilohertz, right? So it's important to recognize that most of these, with the exception of the Neve, are well flat out to 20K, and the only roll-off we see and differences we see are above 20 kilohertz. That's not going to be true of all op amps or all mic pre's. Okay. Here's a few more. Another API, actually this one shows a little bit better the difference. Purple line being low gain, red line high gain. Grace, definitely see a little bit of roll-off. Still, both of them flat out to 20K. These lines are only different because I didn't perfectly match the gain when I made the measurement with my audio precision. They should be right on top of each other. But you can see definitely more roll-off at high gain than at low. And the Millennium Media as well changes its frequency response with the applied gain. Okay. All right, but what I think is the most interesting way that frequency response changes is in this interconnection of equipment, right? So again, we create a voltage divider when we take the output impedance of one piece of equipment and plug it into the input impedance of the next piece of equipment. And if the output impedance or input impedance have reactance, if they have some capacitance, if they have some inductance, like if there's a transformer, then there's a potential that that voltage divider will create a different amount of voltage transfer at different frequencies, which will change the frequency response of the signal that gets transferred from the microphone into the microphone preamplifier. So we're creating this circuit by plugging the mic into the mic pre. All right. Just keep going. All right. Yeah, so when we talk about balanced equipment, this is just happening twice. We have, output impedance that should be matched between pin 2 and 3, and a balanced input impedance that, again, should be matched between pin 2 and 3. But where this gets interesting is how the microphones will react to the load that they see. And this is an example of a ribbon microphone, very simple topology. You have a ribbon suspended in a magnetic field that drives a transformer to step up the current and give you something that can drive a cable into the mic pre. So a traditional ribbon microphone, completely passive, and very, very delicate impedance in that it will interact with the input impedance of the mic pre significantly. So what we see here is some measurements of, I believe, a 44. I forget. I'd have to go back to the paper I pulled this from. And this would be the same microphone driving a 250 ohm input impedance, 700 ohm input impedance, 1500 ohm, and 3K input impedance. So as we increase the impedance that the microphone sees, the frequency response becomes flatter. This no load would be like an infinite input impedance. That's obviously a theoretical line, not actually a measurement. But as you increase the resistance at the input of the mic pre, you get a flatter frequency response. So generally speaking, when you see mic pre's that have a ribbon mode, for example, the Grace has a ribbon mode, the AEA mic pre's are dedicated ribbon microphone preamplifiers. Typically, they have very high input impedances to give you a flatter frequency response with those types of microphones. Yes?
So what other kind of effect does having a crazy high input impedance have on, does it get quieter and quieter as you keep up in that resistance? Or? Like why wouldn't you just have 3,000 ohm input impedance all the time for every day?
Or higher. Well, because a lot of microphones are designed to interact with a particular type of load. And actually, if we go to the next slide, well, skip ahead one more real quick. Now go back. You'll just have to wait for it. One forward, please. Sorry, did you have a?
Yeah. So I was just for the output impedance of a ribbon microphone is that anywhere between 300 and 600 ohms, or?
Well, it depends on the winding of the transformer, typically, but like generally it's going to be between 150 and 600. Yeah. Okay. Here is a SM57. This graph is not from the SM57. It's from a great paper by Southier about designing the EV655 dynamic microphone. Dynamic microphones are extremely complicated beasts because the frequency response of the capsule itself, the membrane attached to the voice coil, is not flat at all. This dotted line shows the original frequency response of just the tensioned diaphragm of the microphone. And the goal of the design, as is discussed in this paper, is to create something that extends the frequency response by adding resonances and dampening to that membrane. So there's acoustic resonators, there's mechanical resonances, and there is a transformer, electrical transformer at the output. But all of those mechanical and acoustical resonances basically interact with the electrical characteristics of the transformer to create a very complex output impedance that can interact significantly with the input impedance of the next stage. Okay, now we get to look at the next one. So here is an SM57 measured loading in black with a 3K load and in red with a 300 ohm load. And you can see that there's very different frequency responses. So each of these, this is 1 dB increments. We have almost 2 dB difference at 120 hertz, a dB difference at 10K. That is going to make a difference in the sound of that microphone, the difference between a 3K load and a 300 ohm load. but the microphone was specifically designed to see a particular load range, right? For me, I use often a Grace microphone preamplifier. It happens to be in the studio, but I really don't love the sound of an SM57 into the Grace pre, generally speaking, because I find it a bit tizzy. The Grace has a very high input impedance, around 6K, so it's going to accentuate the low end and also accentuate the high end, for me, in a not necessarily pleasant way. So, so matching the particular microphone with the particular input characteristics of the mic pre is an important aspect of the sound of the mic pre itself. Yes?
Where is this measured from?
This is, Shure made this measurement for, and we gave it to Peterson. I got it from Peterson. Yeah.
I was just going to say that with an SM57, if you load it down so that it sees 600 ohms, so you have to calculate that on the input to your mic preamp. To me, it sounds the best there.
Yeah, and I think that it's like when the 57 was being designed, I don't know what year it was, but it's an old microphone. They were expecting it to see a particular load, right? So they designed its resonances, they designed its characteristics to see a particular load, and then when you present it with a very high impedance, like 600 or 6 kilohertz input resistance, it actually pushes up the top end in a way that I personally find unpleasant on a lot of sources. But everything has its place. Maybe it's the right thing for some things. Maybe if you want to use that 57 and you have a guitar that's too dark, you put it into something that has a high input impedance. It gives you that extra little high boost, and that's what you want. But knowing that there's this interaction between the mic and the mic pre, and knowing the characteristics of the mic pre, and being able to predict how it will interact with your microphone kind of opens up a whole wealth of creative decisions that you can make in the studio to be able to understand what's going to happen before you do it and make a decision based on your knowledge of what's happening electrically. Yep. We do see a lot of microphone preamplifiers that have variable input impedance. Well, maybe not a lot, but there are a few out there that have variable input impedance. I know, for example, the Mackie Onyx has a variable input impedance. And the first time I used it, I was very frustrated because I was using, I think, a Neumann 84 or something like that. And I was cranking this knob around, and it wasn't making a bit of difference. I think it's probably a 184. Because a lot of condenser microphones have an amplifier, well, all of them will have an amplifier buffering their output. Some of them will have a transformer, some of them will just have an active output stage. But the fact that they have this buffer amplifier means that there's much less complicated output impedance for that microphone. Meaning that when it hits the input of that microphone preamplifier, there's much less potential for changes in the frequency response based on this complex matching of impedances. So when you have a microphone preamplifier that has a little knob that allows you to vary the input impedance, and you do it on a microphone that has a condenser microphone that has an active buffered output, you can be cranking that knob around for days and not hear a damn bit of difference. That, to some people, can be very frustrating. I know I personally found it kind of frustrating when I first encountered it. But back to the 57, if you crank around that knob on a 57, you very likely will hear differences. And so knowing when there's the potential for sonic differences is also useful, so that you don't A, frustrate yourself, and B, you can make good creative decisions. All right, and next. Okay, so of the microphone preamplifiers I've shown, we have a few different input impedances. The Neve 12K input impedance, API 1.5K. Sorry, did I say 12K? 1.2K. John Hardy 1.6K. So all of these sort of, I don't want to call them vintage, but sort of older style mic pre's have sort of less than 2K input impedance. I know George's mic pre is down there as well. But some modern microphone preamplifiers will have much higher input impedances. The True Precision 8, did I say that? Sorry. The True Precision 8 has about 5.5K input impedance. Grace Design, I think I said 6K before. I trust my slide more than I trust my memory. 8K input impedance. So that will change the characteristics of the microphone that you plug it into. Again, Grace's ribbon mode bumps that input impedance up to 20K.
So I have a gap pre, 500 series pre, and it has a switchable input impedance. And the values are 300, 600, and 1200.
Mhm.
In most modern mic preamps, is the input impedance as high as these values? Or because I mean, it seems pretty low, 300, 600, I mean 600 seems like a baseline, but 300 seems pretty low.
It really was pretty damn low.
Compared to this.
I mean, I could see 600 because of the power matching philosophy of the olden days. But 300, I honestly don't know of any designs that's.
I think
Yeah.
it's just there to mess with things, you know. And you can,
I mean, yeah, if you want to really hear a difference, then yeah.
Yeah. Okay.
I imagine it would make your mic darker depending on its
Yeah.
output characteristics.
And
Yeah.
it only affects dynamics, like you said. Like
Yeah,
it's like-
I mean, if you have a condenser microphone that has a transformer buffered output, there's potential for some interaction there, but again, it's going to be much less significant than with a ribbon microphone or a moving coil dynamic that has no actives. Yeah. All right, let's keep going. So noise. How much time do I have? Should I skip over noise? Noise isn't as sexy as distortion.
22 minutes.
What's that?
22 minutes.
Okay, so noise is something that will get into your circuit no matter what you do, no matter how hard you try, and to greater or lesser extent. We try to avoid it by filtering at the input and the output. We try to avoid it by shielding everything in a metal enclosure. We try to avoid it with common mode rejection and creating good power supplies and using good internal grounding. But noise will creep in and will obviously affect our perception of a microphone preamplifier. Next. Yeah, so I guess the big point I wanted to make here is that not all common mode rejection is created equal, and common mode rejection can be frequency dependent. Let's go to the next one here. This is some data. I keep like a running log of data of any microphone preamplifier I ever get my hands on. I do the same set of measurements on. And I'll call your attention just for the moment to the common mode rejection of a few different mic pre's here. The only one here that is transformer coupled is the API. And we'll notice that common mode rejection at 20 hertz is very good. And it gets less good at higher and higher frequencies. Whereas the transformer-less microphone preamplifiers that we have generally have okay common mode rejection at low frequencies, usually because of the capacitors that are used to block DC. Capacitors typically come in 5% or 10% tolerances, so if those are off, they're going to throw off the balancing and therefore the common mode rejection at low frequencies. If you do a good job, though, you can get something fairly consistent. This is our GKL MOPEC, well-matched capacitors will give you a decent common mode rejection at low frequency, but nothing compared to what a transformer will be able to give you down there. And however, the common mode rejection, this style circuit, does give you better performance at higher frequencies than the transformer does. Anyways, enough about noise. Let's talk about distortion. Keep going. Yeah. Thermal noise. Oh, yeah. I don't know. This is kind of interesting. Thermal noise from resistors is a big source of noise. With modern amplifiers, they can approach the theoretical minimum amount of noise, which is, according to Johnson and Nyquist, for 150 ohm source impedance, negative 132, I think, 36? Yeah, dBu. So that's a theoretical minimum. And these amplifiers can actually get close to that, but we need to set the gain of the amplifiers, and any resistor is going to have thermal noise. The higher its resistance, the more noise it will contribute. And most of these circuits are designed in such a way that we have smaller value resistors for higher gains. So in the op amp, the transformer buffered op amp, the lower the value of the resistance in the feedback loop, the higher the gain. In this instrumentation amplifier, the lower the value of this resistor, the higher the gain. So actually at low gains, we have a large contributing factor to the noise of the circuit is the thermal noise of the resistor itself, but it becomes less and less of an influence as we increase the gain. So if we look at equivalent input noises of microphone preamplifiers, often they have better relative performance at high gain than they do at low gain because of the thermal contribution of the thermal noise of the resistors. I think that's interesting. It becomes a challenge to create a microphone preamplifier that has low noise at relatively low gain. But that's just one of the small, subtle problems that can be an interesting thing to try to improve upon as electronics get better and better. All right, let's talk about distortion. Okay, distortion is, noise's much sexier cousin. Noise is unrelated to the signal. Distortion is additional information that is related to the signal itself. So just to kind of get everybody on the same page, I'll talk a little bit about distortion and some of the language that we use. So I will use distortion and nonlinearity interchangeably. If we have a linear system, we can map the input to the output as a straight line. So the little transfer graph here shows the input amplitude versus the output amplitude. In a linear system, that's a straight line. And so if I put a sine wave in, I get a perfectly looking sine wave out. This is 1 kilohertz. So if I look at it in the frequency domain, I get just 1 kilohertz out. I put 1 kilohertz in, I get 1 kilohertz out. I get a perfectly straight transfer function. But if I have a nonlinear situation, I will get distortion, which is the addition of energy at different frequencies besides the fundamental. So if we talk about harmonic distortion, we're going to create extra energy at integer multiples of the frequency of the fundamental. Here's an example of asymmetric distortion. Asymmetric distortion will happen if you have a deformation of the waveform on one side but not the other, right? So this sine wave has been smushed on the top but not at the bottom. Its transfer function is linear here, but up here it begins to roll off. And what that will create is even order harmonic distortion, meaning that for a 1 kilohertz fundamental, I will get harmonics at 2 kilohertz, 4 kilohertz, 6 kilohertz, 8 kilohertz, etc. I'll just take a moment to dispel any assumptions that that this is inherently a tube characteristic and this is inherently a transistor characteristic. That has nothing to do with it at all. Absolutely. Even order harmonic distortion can be created by transistors. Odd order harmonic distortion can be created by tubes. It depends on the circuit topology and the biasing. But what is true is tubes will tend to give you this sort of softer clipping than transistors will. I just used my examples when I said they weren't what I said they were. But transistors will tend to be very linear and then clip all of a sudden, whereas tubes will tend to sort of become nonlinear gradually depending on how the circuit's implemented. I don't want to get too far into tubes because it's outside of my comfort zone. But if we have symmetric distortion, meaning that the top and the bottom of the waveform are equally distorted, we get odd harmonic distortion. So for our 1 kilohertz sine wave, we get 3K, 5K, 7K, and 9K out. Real distortions tend to create both even and odd order harmonics in some combination. Over here, I'm going to be showing some THD versus amplitude graphs as we go along. What this is showing is THD plus N, so harmonic distortion plus noise. This is the signal level that's sent into whatever's being measured. So as the signal level increases, the relative signal to noise ratio improves. So the percentage of THD plus noise is reduced because the relative level of the signal level is getting louder until the point at which the distortion begins to increase above the level of the noise. And we begin to get a little bit of distortion until the system clips. So it's important to talk about the difference between distortion within the normal operational range of a circuit and the clipping characteristic of a circuit.
Just want to make clear, the graph of THT plus N versus amplitude is a system with a fixed gain, and you're adjusting the amplitude of the signal going through that system.
That's right, yeah. So the amplitude gets louder and louder and louder, meaning that the relative level of the noise is reduced until it's loud enough that it's beginning to produce distortion. The distortion increases until it clips, and then the distortion shoots up at the end. But what I'm interested in, generally speaking, and what we should be interested in, we're talking about the color of mic pre's as a result of nonlinearity, is this area here before the clipping, right? When we clip it, we've gone too far. We get a sudden onslaught of distortion that typically we don't want. Maybe in certain circumstances you do want it, but we're just talking about subtle coloration. We're talking about this area in here where distortion has begun to increase above the noise floor, but it hasn't gotten to that point where it shoots up and becomes like a severe amount of distortion. All right, next slide. Okay, a couple other types of distortion. Slew rate limiting happens when electronics can't react fast enough. Basically, you can't create a nice curved sine wave anymore. The waveform will take the shortest path between the zero crossing and the peak or throw of the waveform, giving us more of a triangular wave shape. Anybody who knows about sound synthesis will know that, if you want to make a triangle wave, you have a certain combination of, harmonics in relative amplitude and phase, which give you that wave shape. We also have crossover distortion, which for small signal audio electronics really is not a significant factor. Because of feedback, we can linearize this effect, and typically crossover distortion, even in op amps with push-pull output stages, is not a concern, is not really a contributing factor. Hysteresis is interesting. Hysteresis is something that's going to happen in any device that is reactive. So in capacitors and in transformers that basically store energy in one way or the other, they will have a different distortion characteristic whether or not the signal level is increasing or the signal level is decreasing, which gives it a very particular characteristic of distortion. I did a lot of listening tests in a past life on distortion. I think that hysteresis is a very salient effect. I think it makes the distortion more obvious than if the hysteresis were not there. So that'll happen in capacitors and transformers. They'll have slightly different distortion characteristic. Yep?
Does the different dielectric material of the capacitor affect the amount of hysteresis or the way it sounds? Or
Absolutely.
In audio, I mean, there's the whole like, oh, this sounds better than this. But
yeah. So let's go to the next one here. Okay. So, sorry. So no, it's great. I love when that happens. So different capacitor dielectrics will behave very differently. Some of them are more linear than others. Polypropylene and PET type capacitors are generally extremely linear. High-case ceramic capacitors, not so much. Generally, we don't use those in audios. We might use other types of ceramic capacitors, but the big disc capacitors that you probably see, you just don't want to send audio through them, generally speaking. And electrolytics, they get a really bad rap. This is actually one of the reasons I started researching capacitors. Is there's a lot of mention in literature about how electrolytic capacitors at the front end of microphone preamplifiers have a real negative effect on the sound. And I know SSL, for example, went through a lot to try to mitigate the influence of the sonic characteristics of electrolytics in their circuits. You get, with your electrolytic, you get a fair amount of distortion. So a polypropylene or polyethyl tetra, a PET capacitor will be extremely linear, but are often not available in the same capacitances as electrolytics. For say a 10 microfarad capacitor, polypropylene is going to be very large and very expensive. where electrolytic will be small and much, much cheaper. So, you know, your choice in capacitors will make a difference in the sound. And how perceivable that difference is up for some debate. Typically, we're using these capacitors at the low end, and the ear is much less sensitive to distortion at low frequency than it is at high frequency. So I did a lot of listening tests to see if people could perceive the differences. Everybody could tell ceramic capacitors, but people were having trouble telling the difference at low frequency, so sort of in DC blocking or high-pass filter applications at low frequencies where the difference was between a polypropylene or a tantalum or an electrolytic. So in a circuit, the capacitor will create distortion at around the frequency where it is reactive within the circuit. So if you're creating a high-pass filter and it's reactive at, you know, down at 20 hertz, that's where the distortion will be centered. So let's go to the next slide. So here is a high-pass filter, and we see that the harmonic distortion rises at low frequencies. But with the ear not being very sensitive to distortion at low frequencies, I wasn't able to have people hear the differences between electrolytics and tantalums. And yep.
In the distortion test, did you do anything differently? Did you do some where the capacitors were biased, the polarized capacitors, and then
Yep.
not biased?
I did, actually, and that was one of the reasons. I don't know if you've read that Cyril Bateman paper.
No.
Excellent series of papers called Capacitor Sound. If you go back to the previous slide, please. What happens is when you bias this with like 50 volts, the second harmonic distortion shoots up. So it can increase up to like, you know, almost 20 dB. So one of the reasons I even started researching it was because I was interested, well, what does that mean for a mic pre that uses phantom power and electrolytic capacitors to block that DC? So, you know, does it sound different when phantom power is on versus phantom power is off? Because I could see a distinct difference in the amount of distortion that was produced in the second harmonic with and without the DC bias. The answer was no, again, because all of this distortion was happening at very low frequency. That's my theory anyways. The ear is much less sensitive to distortion at low frequencies. It has to do with critical bands and the critical band rate below 250 hertz, which I won't bother to get into right now. But let's go to the next slide. People were able to hear the difference between capacitors when I used electrolytics versus tantalums versus PETs up at higher frequencies, though, which was interesting. But typically, when we see these capacitors in circuits, they're going to, unless it's an EQ circuit, and generally speaking, I can't think of a single professional EQ that doesn't use PET or polypropylene capacitors, so it's kind of moot. When we do see these capacitors, the electrolytics versus the tantalums versus the PETs, we see them used at low frequencies. Remember back to the original Neve circuit I showed at the beginning, it used tantalums to block the DC and allowed a biasing of the circuit. Yep.
How about silver mica capacitors? You see those used a lot instead of ceramics and...
Well, yeah, but silver micas are the best. I mean, they're amazing, but they're just not available in large sizes anymore. Sure. Yeah, they're great though. But unfortunately, yeah, I'm not sure. They're too expensive to produce. Peter, what's the?
Yeah. Also, you don't see polystyrene anymore.
Yeah. Not in large sizes. Yeah.
Those are really nice just for like feedback loops and op-amps and that sort of thing.
Yeah, that's great. You can get them in small values, but when you're talking about something that allows you to put the input impedance of your microphone where you want it to be where you want it to be, and also not roll off anything within the 20 hertz to 20 kilohertz bandwidth, then it becomes a little dicey. What's available? Okay, next. Okay, so let's talk about distortion now in op-amps. Distortion in op-amps increases with increasing frequency, and this is again related to the gain bandwidth of the operational amplifier. So feedback in an op-amp acts to linearize the amplifier. The more feedback we have, the more linear it will be. But the gain bandwidth decreases with increasing frequency, and what that means is that there's less signal at higher and higher frequencies. This is a gain bandwidth, I think, of a 5534. At higher and higher frequencies, there's less signal to be fed back. Less signal to be fed back means that we will have an increase in the amount of distortion. So here's a measurement of the THD versus frequency of 5534 versus its gain bandwidth product or graph. So what I did was line up 1 kilohertz here, even though they're not exactly to scale. But we can see that as the amount of signal to be fed back begins to reduce, the amount of distortion begins to increase. So we go to the next slide. Basically saying the same things. Here's an example of several different op amps that I measured that all show a similar increasing amount of distortion with increasing frequency. The frequency at which they begin to increase and the amount that they begin to increase really depends on the topology of the op amp itself and its particular gain bandwidth characteristic.
So I have a question about this. So I have the CP5 and that DOA color module. I put an op amp in there. It makes sense to me now why I only hear distortion in that circuit at higher frequencies. I don't hear anything. It doesn't really affect the sound of anything I've run through it at lower frequencies. Is there any, if I increase the gain like tenfold, will that just keep rising, or does it have a cutoff point, or?
No, well, you can imagine. Actually, if we go back one slide, you can imagine the more we increase the gain, the less signals being fed back, the higher the distortion is generally going to be. But it's never like generally it's not going to be at low frequencies. Okay, let's go 2 slides forward here. Here are some comparative measurements of GML, George's op amp, and a 5534. In its FFT, we could see the characteristic distortion. We had a bit of 2 second order and third order harmonic distortion with the 5534. George's has a little bit more odd harmonic than even harmonic distortion, but generally sort of a smooth reduction in distortion with order. Both of them show an increase in distortion at increasing frequencies, but have slightly different characteristics, a little bit different geometry in those graphs. And this is THD versus amplitude. So both of them we see basically where in the gain range we start to see the distortion rise up above the noise floor. So it's in that area up there where we can expect that there's a potential for that distortion to be perceivable and affect the way that we hear the circuit. Okay. Transformers are where we get the low frequency distortion from. So capacitors too, but transformers are much more nonlinear, although people seem to think that they're nonlinear in a pleasant way. Whereas capacitors get blamed for poor audio quality, people seem to like the distortion that transformers create at low frequencies. Derek was actually showing me a product that he has that allows you to switch between different types of transformers, like steel or nickel or iron. Here's an example of the differences in the amount of distortion that are produced with different core materials based on the permeability of the core material used. Typically, steel will have a higher amount of distortion than nickel. I don't have an example of iron here. It really depends on the makeup of the material, but it will increase, distortion will increase with decreasing frequencies. So we see a rise in distortion at lower and lower frequencies for all those different core materials from the transformers. As I mentioned, we need distortion to be higher at low frequencies than at high frequencies to be perceivable, about 12 dB higher really to be noticed. So the threshold of hearing distortion at high frequencies is about 12 dB lower than the threshold for hearing distortion at low frequencies. Next slide. So here are some actual measurements of me brutalizing some microphone preamplifiers to show the example of the contribution of the transformer's distortion at the low frequency and the op-amp's distortion at the high frequency. I will mention there's a certain type of plug-in, virtual bass synthesizers, virtual bass systems that intentionally add low frequency distortion to your signal in order to give you a sense of virtual fundamental. The idea of these things being that if you're playing back music over a small system that doesn't have bass extension, if you have the harmonics of the fundamental, your brain fills in the existence of the actual fundamental. So it's possible that one thing that people appreciate about the low frequency distortion created by these transformers is the way that they eliminate, first of all, excess subsonic frequencies that you don't need, tightening up the sound, but also give you this increased sense of low fundamental presence, even if it's not actually there as much based on the harmonics that it generates. So what you see here are the Neve API, Hardy, and basically a transformerless integrated circuit instrumentation amplifier mic pre, all compared. In the red, I have the maximum gain, and that means I'm sending in a low-level signal to get a high-level output, plus 25 dBu output. So the contribution that you see in red is mostly from the output transformer. You see the distortion from the op-amp and distortion from the output transformer. But in the purple, I use the minimum gain and the same output level. That means I'm driving the input harder, and you're going to see more of the contribution of the input transformer, but obviously you're still also going to see the output transformer. So when the circuit's all there, it's a black box, you're measuring it, you don't have that many options to isolate these things, but you can kind of see the differences. Now, normally we're going to be running them at the middle of their characteristic, and most of these are relatively flat. We get a bit of the smiley face in the Neve. I don't know about that API measurement if I trust it, honestly. That looks like it might be a bad measurement. And a little bit of smiley face in the Hardy, not as much as with the Neve. But it's really when you begin to push these things that you start to develop those potentially perceivable harmonics that might color your perception of the character of the mic pre. Next, I kind of forget what's happening next. So same mic pre's compared again with THD plus N versus amplitude. All three of them are very linear until they clip in the mid frequency. But at low frequency, we see the distortion of the Neve and API causing this area where the distortion rises up above the noise, potentially coloring the sound in the lows. And in the Neve and API, again, we see the same thing, a rise in distortion before the clipping point at high frequency that, again, has the potential to color the character of the sound. Next. All right, so just to kind of recap everything, I think I'm probably running out of time anyways. I still believe that the most significant factor in the sound of these mic pre's is going to be the potential alterations of the frequency response, whether it be because of the interaction between the output impedance of the mic and the input impedance of the microphone preamplifier, or the intentional roll-off of high frequency and low frequencies by the designer, or unintentional side effect of the gain bandwidth characteristic of the amplifier. Changes in frequency responses are going to really contribute to perceived differences between mic pre's. But noise and distortion also can play their part, and I know that distortion is one of the more fun things to play with in terms of what we can do in order to change the sound of mic pre, and we'll be talking later this afternoon about our mic pre and how it interacts with the color module series from Peterson out of DIY.RE, and how we can use the distortion's ability to color the sound for creative ends. But in the case of the microphone preamplifiers compared here today, we definitely see the potential for the distortion at low and high frequencies to be a contributing factor to the differences in the sound quality, but mostly at high output levels. Yeah. Anyways, all this information hopefully will help you make more creative decisions when you've got a mic pre and you got a mic and you need to plug it in somewhere. Thinking about the input impedance, thinking about the distortion characteristic, thinking about where you're going to be running it in the gain range of the mic pre, all can contribute to what choices you're going to make in the studio. Yeah. Thank you.